Okay, so Assalamualaikum semua. So this is our lecture for today. Okay, so this is design via root locus. The title is kita dalam week online 5 now. Okay, design via root locus. So we're going to go straight away to point number 1. Okay. You remember yesterday saya dah I presented to you yesterday. We talk about the this is the closed loop block diagram. Okay, the closed loop block diagram. So we have the forward system, open loop forward system here, open loop system, and this is GC here is the controller. Okay, so what we are going to focus on for this lecture today is this one for GC controller. Okay, yesterday we have talked about gain adjustment. Okay, gain adjustment, which is actually a proportional controller. So if you want to revise on the lecture yesterday, you can also look at the textbook, which is on the transient response design via gain adjustment, example 8.8. Okay, so and also yesterday we talked about proportional plus derivative, which is PD compensator yesterday. Okay, we covered that also. So if you want to do your revision, if you you can look at example 9.3, chapter 9, which is improving the transient response via cascade composition. So what we're going to cover today is the PI compensator, which is a proportional and integral compensator, where in this one we are improving the steady state errors via cascade compensation. So we're going to look in detail. We're going to discuss example 9.1. Okay, so this is an example of the closed loop block diagram, and example of system which is yang kita selalu cover, we talk about is the elevator system here, and also the antenna position control system. Okay, so let's focus on example. Straight away go to example 9.1. Okay, so we are now in the topic of transient response design via cascade compensation. Revision about yesterday. Okay, so given the antenna position control system, this antenna position control system, the antenna has the forward transfer function GS equals to 1 over S plus 1, S plus 2, S plus 5. Design an ideal derivative compensation to yield a 25.38% overshoot with 30% reduction in settling time. So this is one example of designing a control system. Okay, so the questions, it already gives you the constraint, the design requirement, which is the design requirement is 25.38% overshoot. Okay, 25.38% overshoot, and a reduction of a reduction of settling time to 30%. Okay, so example of antenna position control system is this one. Okay, so it needs to position the antenna to move to the desired desired position that we want. Okay, so this is example of this is one design example that you can use a PD compensator. Okay, so what does it so let's look at how we solve this problem. Okay, so what we need to do is we need to design the controller. Okay, let's look at how we solve this problem. Okay, all right, so the problem is, this is the problem that we restate the problem, and this is the antenna position control system. So where GS here is 1 over S plus 1, S plus 2, and S plus 3. Okay, so this is the GS. So the antenna system is here. So we need to design the controller GC here in such a way the question asks you to design a derivative compensation. So a derivative compensation, then it will be a PD, P plus D. Okay, and the design requirement is you need to achieve the output that you need to achieve. Sorry, this is C. Okay, so the output that you need to achieve here is the overshoot is 25.38%. Okay, and the setting time must be reduced to 30%. Okay, so So what are the steps for you to perform this? So these are the 4 basic steps that you need to do. Okay, we call it design methodology. So the methodology to solve this problem, right? So the first one is we need to evaluate the stability of this system, GS. Okay, so the stability of the system, where in this part you can use chapter 6, which is you can use Rutherford, you can use Rutherford table, and also use Rutherford table. Okay, we're not going to cover that for number 1, but it's the basic procedures that you need to evaluate first the stability of the system before we want to design the controller. Okay, as simple as a human, you cannot control someone to follow you if that person is tak stable, tak betul, right? That's the simple analogy. Okay, so we go straight away to number 2, analyze uncompensated system. Uncompensated system here means that GS here. GS without the controller. Okay, so in this case, the GS is equals to K over S plus 1, S plus 2, S plus 5. So we analyze the uncompensated system first. We need to know the system first before we design the controller. So we need to know, okay, the current system, what is the settling time? That's what we need to know. Then we can design the 30% reduction of the settling time. Okay, so third is we design the controller, which is GC here. Design the controller, GC. Okay, so this is third. And number 4 is then we analyze the compensated system, where in this case now, since we are using GC PD, so you know that PD will be S plus DC. So the compensated system will be K S plus DC over S plus 1, S plus 2, S plus 5. Right? So let's look how we solve it. Let's look at the second steps. So analyze the uncompensated system. So from this equation, from this system, we draw the the root locus. Okay, then from the root locus, we are able to analyze the certain parameters, which is we have talked in detail yesterday, right? We can analyze the peak time and also the settling time, right? Settling time. So the peak time. So if you can see here, and then the question asks you want 25.38% overshoot. Okay? So by now you should know how to convert from 25.38% overshoot, transform it to a damping ratio. So in this case, the damping ratio is 0.4. So using the MATLAB, okay, MATLAB, so you can able to get the root locus, and the MATLAB can help you to get the root locus. So your task is you have to know how to analyze the root locus. All right. So in this case, you have 2 poles. You have 3 poles here: S plus 1, S plus 2, and S plus 5. So there are 3 open loop poles: S1, 2, and minus 5. So from this open loop poles, it gives the zeros, the blue line, which is the closed loop zeros. So as you can see here, there is only one root locus that intersect with the damping ratio 0.4, right? So the point that this root locus intersect is at minus 0.939 plus J 2.151, and at this point the gain is 23.72. Okay, so all these things we pick up, we put it in the table. Okay, so the analysis, we can put it in the table. So where the gain K is at 23.72, and the settling time here is from this, we get the settling time. The settling time will be equals to 4 divided by 0.939. Can you help to calculate for me whether it's correct to get 4.26? Can someone help to calculate?
Betul, ma'am.
Betul, eh? So the peak time is 5 over 2.151. So can you help to calculate the peak time? Betul?
Betul juga.
Betul juga. Okay, thank you. Alright, so then we already done the second step. So next one. Then we're gonna analyze the compensated system. Okay, so for the compensated system, this is not right. Okay, so it's supposed to be K here, S plus ZC for PD. Okay, So the C here, yesterday I already talked with you, elaborate a lot about this. What is the ZC here, the zeros here? The zeros, we try and error, we can have the zeros at somewhere around here, -2, -3, -3, -2 and -5 for example. We can have the zeros around here, but today untuk nak just to review, a quick review, we're going to go straight away to the final answer, to zeros at -2. So for the analyze the compensated system, so the compensated system now we're going to add the element of zeros here. Okay, so zeros here, in this case, it puts at -2. So what happens, bila zeros at -2 here, it changed the root locus, right? It changed the root locus from initially the root locus is curvy like this, when the uncompensated system, but with only 1 zeros here and zeros at -2, the root locus change to get this like straight root locus, okay, this form into this shape. So and now the root locus intersect the damping ratio at this point. Okay, intersect the damping ratio at this point. So we can put, and now we are ready, we can have the information about the setting time and also the peak time, right? So then here in a table, we put it in the table, make a good practice, make a practice that everything when you have from the root locus design, you translate it into a table, okay? So now the GS now is a compensated system. K, which is K S plus 2, which is the cascade compensation here, over S plus 1, S plus 2, S plus 5. And from here you get the gain K is at 51.25. Okay, and the settling time is 1.33. Because of these zeros, you get the settling time at 1.33. Can someone check for me? So start. 4/3. Is it correct, 1.33? Is it correct, 1.33? Betul. Okay. Yes. Okay. So it's correct, 1.33. So this is what we get when we have zeros at -2. You can explore what happens if you have zeros at -4, at -5. You can always explore when you are using MATLAB simulation. MATLAB, okay, using MATLAB software is easy for you. You just know how to do the script. Okay, so you just know how to do the MATLAB script, and you can try to put zeros at -4, -5 and run it, and then you can get the root locus and you can get the information from the root locus. Okay, all right. So we compile both results. So now let's talk about the results. Okay, so for the uncompensated system, look at table 2, which is a comparison performance specifications of antenna position system. Okay, so when it is uncompensated without the controller, it means that without the controller, it only has the gain. So the gain at 23.72 will produce a settling time that will produce an output response here. Okay, will produce an output response here that will give the setting time 4.26 and the peak time 1.46. So which is the black color here. Okay, but when we have a PD compensated where we only add 1 zeros at the numerator here, what happens at gain 51.25, we are able to get the output response with 25.38% overshoot. Okay, we are able to get the output response 25.38% overshoot, and the setting time we are able to speed up the response where the setting time will be 1.33 and the peak time will be 0.46. Okay, these results here is actually we are able to get the same percent overshoot here. It means that this is here, so the output at 0.2 it will be like this. Okay, so the percent overshoot will be the same. Okay, but the peak time will be faster. Okay, and the setting time will be faster. So just check, is it for this compensated system, does it achieve 30% reduction in setting time? Does it achieve 1.33 over 4.26 times 100. What do you get?
31.29.
Okay, so 31.29%. So it's almost achieved 30%. It's almost achieved 30% reduction of certain. Okay, so you meet the design requirement. So those are the steps to do the design. Okay, so what it says that for this antenna position control system, if you have the controller, okay, the GC here, the controller here, we put it at K S plus ZC, where the K, we tune the gain K at 51.25, okay, and your ZC, sorry, ZC is at and your ZC is at -2, you are able to get the output here, the output response here. Okay. You are able to get the output response like this, which has a 25% overshoot, and the peak time is 0.46, and the setting time is at 1.33. That's what it means. Okay, so it means that without the controller, it may take, for example, we want the antenna to move from 0. So for example, we want the antenna to move from 0. Okay. We want the antenna to move from position, okay, we want the antenna to move from position 0 to position, what happened here? From 0 degree to 90 degree, for example, right? So without the uncompensated system, without the controller, okay, the antenna will take 4.26 seconds to reach 90 degree. That's what it means. Okay, and at this time, the gain, provided that we tune the amplifier gain here, we tune the gain here to 23.72. If you tune the gain to other values, then you will not get this performance. Okay, but if you have the compensated system, it means that you design the controller, okay, and you tune the controller to 51.25 gain, and you have the zeros at -2, you are able to make the antenna move to the desired position to 90 degree at a faster time, which is 1.33 seconds. So that's what it means. Okay? So far so good? Okay? So this is for cascade compensation. Okay, let's move to our lecture today. This is the summary about from yesterday. Okay, so let's move to our lecture today. So yesterday we are talking about improving the transient response here. Okay, we are talking about improving the transient response, which is this one. This is yesterday, and this is yesterday. So today we are talking about improving the steady state errors for today. So that's why I'm giving you the quiz first for the steady state errors, partly for you to do revision about the steady state errors and some important formulas that you need to know first before you are ready to design the steady state, the controller that will improve the steady state errors. Okay, so this is actually some revision, the quiz that I give you. Okay, so for this one, what is your KP? So using the formula for KP, which is, I'm going to do here, the limit GS over, the limit GS, so which is your S here, will be approaching 0, which is equals to, here kita letak K50, right? So 50 which is 1.5 over 0, 1, and 10. So then you will get your KP equals to 1. Betul tak? Sorry, 7.5 over zeros. Dapat berapa?
Infinity.
7.5 divide by zeros. Berapa you dapat?
Infinity.
Infinity. Itulah. I think this one is something not right. Okay. So KV. So KV, what is the formula for KV? Again, we're going to limit our transfer function S to 0, but now we have an element S here. You see that? Okay. So what is this element? So what it means is that we're going to have K 50 1.5 over S is multiplied by S here, so we will just have 1 and 10. So this one you will get 7.5. Betul? Okay. So what is KA? So KA is now we're going to limit our transfer function, but now S multiplied by S to the power of 2 and S is approaching 0. So what it says here is that we're going to have 50 X 1.5 over 1 and 10, then you will get, what we will get?
Yeah.
Huh? Betul tak?
0.
Alright, so what is the step input? So for the step input is 1 over 1 plus KP for the step input. For the RAM input, it will be 1 over KV. Okay, the error for the RAM input and the error for the step input, and the error for the parabolic input will be 1 over KV. Okay, those are the things that you need to understand first. Okay, for this one, we already talked about the table 7.2, right? Table 7.2, we're talking about, okay, for this plot diagram, what happens if we have a step input? So for we have a step input, okay, so the steady state error formula is 1 over 1 plus Kp. Okay, so the type, if it is the system, if GS is the type 0, it means that, okay, you can get for a step input, you will get some error. But for RAM input, it will be infinity. You cannot get the error. So for parabolic input, you also cannot get the error. Okay. But if the system is of type 1, okay, so you give an step input, you will able to get the error equals to 0. But if you give a RAM input, you will get some errors of values, but it's not going infinity. Okay. So if the system is of type 2, okay, if you give parabolic input, a RAM input, you will able to get the error equals to 0, and the parabolic input, you will get some values, okay? So the error will not go to infinity, but there is some values to the errors. So these are the foundations that you need in order for you to be able to design PI controller, okay? So in order for you to design a controller that is able to improve the transient response need, the steady state error. Okay, so again, sorry, this is not transient response, this is steady state error. Okay, in order for you to improve the steady state error. So I'm looking now at if you want to look at the textbook, it is at page 459. All right, so let's look here a little bit, okay, about this how the block diagram and the S-plane. Okay, for example, you have the plan. Okay, the plan here, so it can be an antenna dish. Okay, the complete system of antenna dish with the motors and everything. Okay, so you have the gain here. So, for example, for this plan and with this gain, the root locus is like this. So it means that there are 3 poles, open loop poles, and these 3 open loop poles will create a root locus that is moving at the positive and negative, and the A here is at this point. So now is what happens if we add an integrator to the gain here, to the controller here. Okay. Now for B, we add an integrator 1 over S here to the controller. So what happens that when you add an integrator, it means that there will be 1 pulse X zeros at the origin here. There will be 1 poles at the origin, sorry. Okay. So there will be 1 poles at the origin. So what happens? Adding 1 poles at the origin will change the shape of the root locus. As you can see here, due to this 1 poles, the root locus now becoming 2 branch, okay, and it is diverging. One is diverging to the positive here, to this side, and another is diverging to this side. So if we maintain the point A here, you can see that both locus will not intersect point A. So what we need to do to make it intersect? Okay, so pole of point A is on the root locus without compensator, it says here, and pole of point A is in the root locus with compensator pole added. So what we need to do to make it intersect? You see here at the controller we add 1 zeros A here. So the zeros is somewhere that is near to the roots here. The zeros here is near to this. Okay. So what happens if we add the zeros here? When we add the zeros, we are able to have the root locus that intersect again the point A. Okay. So the pole of A is approximately on the root locus with compensator pole and 0 added. Okay. So this is what we talk about. This is what we call a PI compensation. Okay. So we call a PI compensator, or we call it a PI controller. Compensator and controller are both the same things. Either we compensate, but in the industry we don't say a PI compensator. In industry, in real application, we talk about controller, a PI controller. Okay, in the theoretical part, we are talking about compensator. Okay, so let's look at directly to example 9.1. Okay, so we have a problem here. A problem given the system in figure A, okay, which is operating with a damping ratio of 0.174. Show that the addition of ideal integral compensator shown in figure B reduces the steady state error to 0 for a step input without appreciably affecting the transient response. So what the question asks you to show. So what is it to show? Okay, so the information that we know here is that the damping ratio for these plants is 0.17. Okay, and we need to design. Then it has an ideal integral compensator. So here it has a PI controller. Okay. When it adds the PI controller, okay, we are able to give the steady state error to 0. So the error here should be 0. It will be 0 for a step input. Okay, without appreciably affecting the transient response. It means that the transient response TS1, TS2, so this one is TP1, sorry, TS2 and TP2. TS2 will be something like TS1. So it's not affecting the static time here. Okay, so this is TS2 and TP2 is equals to TP1. So that's what you know. Okay, for the step input. So let's look how we solve this problem. So this is the design methodology, how we solve the problem. Again, there are 4 steps here. So above, the first one is we analyze the uncompensated plant. Okay, so we analyze the uncompensated plant and then we evaluate the uncompensated plant steady state error for a unit step. And then we analyze the compensated plant and evaluate the compensated plant steady state error for a unit step. So there are 4 steps here. So let's look at the first one. Okay. So the first one, when we analyze the uncompensated plants, we know that we have 3 poles. Okay. 3 poles here. S plus 1, S plus 2, and S plus 10. Okay. So the root locus will have 3 poles, minus 1, minus 2, and minus 10. So this is the root locus that we get. Okay. Again, we can use MATLAB. Okay, but you also need to know how to sketch this root locus using pen and pencil. Okay, so for this root locus, the question asks to get, we're looking at the damping ratio of 0.174 here. Okay, so we sketch, we put the damping ratio 0.174 here, and we see that the one locus, one root, one point that intersect, the root locus intersect 0.174, which is at minus 0.694 plus 3.926. At this point, the gain is 164.6. So this is for this one and this. Okay, for the uncompensated system. Okay, so next is we design the PI controller. So we know that the PI controller will be GC will be K S plus ZC over S. Okay, so in the poles, so we know that we're going to have for poles, we're going to have one post at 0, and for zeros, it will be at minus ZC. Okay, so this is, in this case, this is the zeros and poles here. By adding the zeros and poles here, okay, then the zeros, which is very near to the poles, so for sure that the poles is at 0, at point 0 here, and we have the zeros here that is very close to the poles. What we get is that we are able to maintain the shape of the root locus. Okay, maintain the shape of the root locus, and we are able to get the root locus intersect, the root locus still intersect at the damping ratio 0.174, but now the gain is slightly smaller than the gain that we get previously, which is 164.6, but now the gain is at 158.2. Okay, so let's combine, we combine everything. And we know that when we look at the table, the steady state error table, so we know that as we add the integrator here, we are actually adding the type of the system. We are actually changing the system type, which is initially type 0 to type 1. Okay, due to the integrator here. So from the table, we know that if it is type 1, it means that with a step input, okay, with a step input, you will get a 0 error, and if a ramp input, you will get some constant value here. Okay, so for this case, it already tells you that the input to this is a step input, I think. Okay, so you know that to get the steady state error to 0, and we can increase the system type to type 1, and then we can get, using the step input, you are able to get the steady state errors to 0. Okay, let's look at the conclusion on this. Okay, so what it says here is that the compensated system with its poles, the compensated system with its poles at the origin becomes a type 1 system, so it will respond to step input with 0 error. Okay, so what, in terms of step response, what do we get actually? Okay, we are getting that the uncompensated system, it goes there is some transients in the uncompensated system, and after like few seconds, it will goes to steady state, but the steady state has some errors. Okay, so example that for this one, the desired set point is at, the step input is at 1. Okay, so for the uncompensated system, there is some errors here, okay, which is not equals to 0 for uncompensated system. But when you design a PI controller, you are able to make the errors equals to 0. For the compensated system, you are able to make the errors equals to 0. Okay, so this is what happens. Okay, but at the same time, the transient response, the speed at the transient response remain the same like the uncompensated system. Okay, so the transient response of uncompensated and PI compensated system is same up to approximately 3 seconds, and after that time, the integrator in compensated system slowly compensates for the error until 0 error is finally reached. Okay, so the element of 1 over S actually, GC, S plus ZC over S. This S actually that integrates all these errors to become 0. Okay. Okay. So this is what it means. So in conclusion, it's actually we are talking about just now the design of PI controller. So what is it actually? Mathematically, the PI controller will have a proportional here that is added with an integral here, 1 over S, and both will be will feed forward to the plant to control the plant output. Okay, so it is able to, with this PI controller, we are able to improve the steady state error. Of CT, of the output. Okay, that's all. So far, ada apa-apa soalan? Any question?
Ma'am.
Okay, so that's all for PI controller. So kita dah cover PI, PD,